Okay, ready to go? So how are we doing on the homework? Do we need more time? Or good? Yes, we can. So, but next week is very short. So we have a, if I remember correctly, we have a review session on Tuesday, right? And the exam is when? Friday or something like this? Friday. I forgot the time, but so it will be dense. So I'm okay to push the homework as far as you guys willing to go, but at some point you should switch and start working on the exam, right? So what is the good day? Monday for the homework or more? Monday is good. Okay, let's push it to Monday. So I mean, I will also assign one extra credit assignment about file systems. So it's optional, right? But if you want to boost your grade, you can do it. Okay, so let's switch. So today our goal is to quickly finish discussing of the synchronization primitives and how they are used in the x86 kernel, and then switch to file systems. So essentially just start going for file systems so we can understand what the role of the file system and how they are organized. So last time we talked about spin locks, right? So we understood why we need them. We know how machine runs multiple CPUs. We know why we need to synchronize to implement these critical sections. And in this very short section, I will try to explain how we can use those spin locks to implement a pipe, right? Because pipe is conceptually something, remember what it is. It connects two processes. One process can write into a pipe, another process can read from a pipe, right? And not surprisingly, since we know that x86 bootstraps multiple CPUs, the read and write ends of the pipe may run on on two different CPUs, right? Is it clear to us that it can happen in practice, right? Okay, so let's first consider a very simple, it's kind of like a very kind of rudimentary communication abstraction, which will lead us to a pipe. But let's just take a look at it first. So this is the very simple, you can call it a pipe if you like. It takes only one pointer. So you essentially can write one pointer into a pipe, right? Not really a pipe, but communication mechanism, right? So this is the queue data structure, and the only field it has is a pointer, right? And you say, look, I can send something into this queue by providing the queue pointer and the pointer I want to write. So supposedly, maybe you have some data here, right? But you say, the way it works for me, I just essentially just write this pointer, right? And the way this send works, right, is that it says, okay, if the pointer is empty, if the pointer is not empty, I'm going to spin here, waiting for someone to receive the previous pointer from this queue, right? And the moment it got received, we say, okay, look, there is this, we assign this pointer here, and the send is done. Receive works symmetrically, so it essentially says, okay, it takes the queue as an argument and returns the pointer as the return value, right? And it works kind of similar to it. It says, okay, I will try to read the pointer from the queue. If it's empty, I will keep spinning. If it's not empty, it gets assigned. Then I say, I acknowledge the fact that I received the pointer and I return P, right? Do you see how it works? So you can send a pointer one at a time through this queue, right? And from that, we will quickly get to a pipe. But let's just first consider how this thing works. Okay, so that's my explanation. This is totally fine, right? So this communication primitive actually works. Although, remember, last time we considered various, like we considered a couple of cases, so specifically a linked list, right? And the linked list did not work without spin locks, right? Without a critical section. But this thing works, right? So if you carefully inspect the source code, you see that the two threads or threads of execution can perfectly synchronize on this thing, right? The only problem which we have here is this spinning, right? So essentially here, if the process tries to send something P1, it might spend the entire time slice, right, just spinning on this while loop, because maybe this process P2 is not yet ready and it did not receive this pointer, right? So it just didn't get to this point yet. And it's somewhere in the queue of processes. The operating system will schedule it later. So, but it's very easy to lose time here, right? It's not always the case. So sometimes you actually design systems in such a manner that processes are scheduled. It's called gang scheduling. So they're scheduled to the group, and the whole group is actually scheduled at the same time. And this communication is really, really fast, because you say, look, I might be like, I know that this guy will be running very, very soon, and maybe it picks up messages like every 1,000 cycles or something. So the max amount of time you will be spinning here roughly is 1,000 cycles. Agree with this? But okay, but imagine this is not the case, and we don't have this group scheduling, right? And instead we say, okay, can we figure out a trick to avoid spinning here? Imagine you reach this line, you see that the queue is still occupied. So what do you want to do instead of spinning? What's your meaningful strategy at this point? What is this message? Some kind of a signal. But what needs to happen to this process, P1, who is a sender? It can sleep. So what does it mean to sleep? So what we want to do here is we say, look, we want to yield the CPU, and maybe the whole thing is just running on the same CPU. Maybe P1 and P2 will be running on the same CPU, right? So you say, look, I want to yield the CPU, and you say, and we'll go and sleep, meaning I will be waiting for some kind of a signal when I will be woken up later on when the queue is available, right? That makes sense. Okay, let's do it. So we introduced the following communication primitives. So asleep, and it can take, roughly speaking, some vague argument, like a number, which represents the event on which, or channel on which this process is sleeping. And a wake up, right? So, and a wake up will wake up everyone who is sleeping on that channel. Meaning, so when a process invokes sleep, it is transitioned in the proc state will be something sleeping, meaning that the scheduler will not try to schedule this process. It's not runnable. And we remember how the scheduling code works. And before doing it, it will set something like proc channel will be equals to this number channel. And later on, when someone comes and says, when some other process comes and says, wake up, the wake up will look through all the processes in a sleeping state. And if the channel match, then this process gets woken up, meaning that its state gets updated from sleeping to runnable again. Right? Makes sense? Okay, so this seems to be useful, and we want to do something like this, right? So the sender, for example, says, okay, imagine like we get the fact that the queue is empty. We write the pointer into the queue, and at this point we say, please wake up all the receivers, right? Makes sense, because maybe they are waiting on this. Maybe early on, instead of like spinning here forever, the receivers they went to sleep essentially, right? Make sense? So this avoids essentially endless spinning here, right? Agree? Will this code work? It's okay. Like they all get woken up. It's a valid case. So multiple processes can sleep on the same channel, and you will see use cases when it's useful later on. Agree. Right. So where's this race condition? Can you be more specific?
Like you send a wake up call. Now it hasn't started sleeping, and the wake up send sleeps right then.
Correct. So what happens here, okay, what your classmate is saying, okay, imagine this guy essentially got to this line, 2007. Meanwhile, no, let's say not 2007. Let's say it got to line 2005 or like right before 2006, right? So this hasn't yet happened, right? This right. Let me erase everything. So we're about to execute this line in this process. And meanwhile, the receiver says, okay, I'll check the queue status. It's 0, right? Because this line has not yet happened, right? And I go into this while loop about like hoping that I will go to sleep, right? Meanwhile, this guy executes this and this line, sending a wake up. It goes and it tries to wake up everyone, but sleep has not yet happened, right? And at this point, this process later on goes to sleep, and we are in a deadlock because this guy went to sleep. Next time this guy comes here, it will be essentially spinning on this queue forever, right? But we'll never send a new wake up. Agree with this? It's called the lost wake up problem, right? So essentially, this is the visualization here. So one guy does, receiver does the test, and this is the timeline. Meanwhile, the sender updates, so test says, come, okay, the queue is empty. So it's about to go to sleep. The sender, meanwhile, stores the pointer P, sends a wake up, right? And wake up never wakes up anyone because no one is yet sleeping. Meanwhile, this guy goes to sleep, and it will be waiting for the wake up forever, right? So this is the problem. Nature think, okay, can we fix it? Obviously, this is a synchronization condition, which is wrong, right? So we got into some kind of a deadlock here, right? So can we fix it like this? Or how can we fix this problem? You say that move this line here. Before 311, okay. No, okay, first of all, what's wrong with this solution? Who can tell?
It requires the logic in this semester going for the other one. That has to be the
No.
He was like, a lock, you won't be releasing the lock, like we are uniquely going to sleep in 320.
Right, so this is the problem. So here, if you acquire the lock here and you go to sleep, then you're holding the lock, right? So which means that if you try to do the send, you will never acquire this lock here, right? So this is a deadlock. So you suggest, okay, let's move this line to before 311, right? Let's take a look at whether it will work. If you put acquire here, if we put acquire here, then it seems that it's the same problem. So if this guy went to sleep, this acquire will never work, right? So this doesn't work, right? What kind of trick we can do? What do you think?
Before going to sleep, I can't release the lock. Someone wake up, right? Then again, get the lock.
Before going to sleep, why can't we release the lock? And yes, this is kind of what we were doing. This is the good insight. What we will do here is we extend the sleep call with the lock itself. with the intent to release it, right? But there is still, there is a, like, if inside the sleep you release the lock, you can still end up with the same race, because this guy can acquire the lock. Imagine you didn't yet go to sleep, right? But you release the lock, then again, you can lose this wake up. So we will orchestrate in such a manner that we'll introduce another lock to make sure that the wake ups are atomic as well. But at a high level, the idea is the following. So this sleep will take the lock and will release it internally to make sure that the wake ups are not lost. Okay, this is how it works. So what we're doing here is we first, inside the sleep function, we first acquire yet another lock. And this lock will prevent other wake ups from happening, right? Because the wake up will try to acquire this lock as well, right? It's called a P table, process table lock. It's essentially like all operations on processes are guarded with this lock. So if we acquire this lock, then what we do here, we can release the lock, which we got as an argument here, right? This is our sleep lock, right? It's safe because at this point we already acquired this P table lock, meaning that, okay, if someone tries to send a wake up at this point, that someone will be spinning on this lock, right? And what we do here is specifically, we do what I was saying. So like we remember the process, the channel on which the process is sleeping. We remember that the state of the process is sleeping as well. We enter the scat function, and the scat function will try to essentially pick a different process to run. But the safety of this lock is the following. So when someone tries to do a wake up, it says, okay, look, we have to acquire the P table lock, right? So essentially at this point, this guy will be waiting for the scheduler to finish, and the scheduler will, on the other side, when it context switch to another process, it will release the P table lock, and only after that this wake up goes through, and essentially like, well, this is how the wake up one runs. So essentially, it looks through all the processes in a system, checks that the state is sleeping, channel matches, and then switches them to runnable, right? That's essentially the synchronization paradigm, which allows you to avoid this race. And at a high level, the invariant which we have is that this cat function is executed with the P table lock acquired. So it acquires a P table lock, and it will always release it, right? Which means that even if you went through this pass from process P1, went into the scheduler switches into this scat function switches into the scheduler itself. The scheduler here, it knows that it picked the new process, switches into this new process, and inside this new process, you exit from some kind of a function, and there will be a release of this lock. So essentially, across the context switch, the lock will be acquired, right? Okay, you got the gist. So the book actually describes it as well. So again, read the book and make sure that you understand all the code paths through the context switch, and understand that the P table lock is always acquired. But the goal, again, the high-level problem which we were trying to solve is to prevent this lost wake-up. So essentially, that's the solution. Good.
Something like we are acquiring a lock on one of the stack and releasing another stack.
Right. So why does it work?
Same process.
No. What are we acquiring? Like if I ask you a question, where is this P table lock? Like this one. Where is it located physically? In which memory? Kernel, yeah, I get it, but like which section? Data, heap, stack? Data, why? Correct. So it's a global variable. So it's allocated in the data section, right? Which means that, like, this is the data section of a kernel. This is the log. On one CPU, one process acquires it, right? It can very well be possible. I mean, if you acquired it on this CPU, since you already have a control, meaning that, of course, you go into the scheduler does the context switch. You switch the stacks, but the global memory doesn't get switched, right? And so still, when you do a release, it's again release of this log. Meanwhile, some other CPUs might be waiting for this log saying, okay, we also want to do a context switch. So we want to do acquire, right, of this log. But this is essentially the cache line. They know this cache line. It's a single cache line. It contains this value 0 or 1. And it might be bounced multiple times, might be checked, but at some point the release says, okay, we switch it back to 0. And then this guy might be able to write 1 into it, right? Good with this? So it's not on a stack because, yeah, if you have multiple copies of logs with the different logs, then you have to be careful. I mean, you can allocate this log on a heap, but just make sure that it's known to everyone, to every process in the system somehow. So there might be some other like global variable which somehow allows you to resolve this location. Right? Okay, this is clear. Okay, so if we build this very simple send receive primitive, let's quickly go through pipes. I mean, remember pipes. You can do a write, sorry. Oop, somehow that one stopped working already. You can do a write. In a file descriptor, you can pass a buffer, pointer to a buffer in user level and a len of this buffer. And if this file descriptor in the kernel points to something what is a pipe, right? Then what happens? Remember? What's the behavior of a pipe? We write the maybe partially, depending on how much space we have here, because the space is limited, right? And in our case, it's 512 bytes. We write part of it into the pipe and essentially allow someone else to read from this pipe. Have a read function which says, okay, there's a file descriptor, there's a buffer where I want this data to be, and there is a len of the buffer, and this file descriptor leads to a file here, and this file points to the same pipe, right? So essentially, this guy will pick up some number of these bytes, which will fit into the buffer, and we'll copy them here, right? So, and this is in two different processes, or can be in the same process, P1 and P2. But when we drop into the kernel, right, there's a system call. So that might be a difference. So this is a proc and a file descriptor table, right? And this is a file descriptor table of a different process, right? But at this point, they point to the single pipe. It's a single data structure in a kernel, and they communicate through this data structure. Agree? So now I will explain how we build this data structure. Question? It can be on a heap of a kernel, but the way I think, so depending on how much source code you read through x86, or you read in the x86 kernel, you might have noticed that x86 doesn't have a memory allocator. So it doesn't allocate processes. It has this process alloc, essentially has an array of pre-allocated processes, and it just picks one available array. So it does the same for the pipes or for the files. So it's essentially says, okay, by the way, I have like some finite capacity. I have like 16 different pipes I can open, or maybe 64. And so since it's allocated statically, it will be in a data section. Although modern kernel like Linux will probably keep it on a heap, right? But in x86, it's in a data section. Correct.
And where does this memory share? I mean, we have a share between P1 and P2, right?
Yeah.
So the complete data structure is
correct. So all of these guys, process and its file descriptor table, if this is the file and this is the file, all these data structures will be allocated in the data section of the kernel. So there will be like a process table, and there will be a file table. It's a little awkward, and there will be, for example, pipe table, right? And it's not how a typical modern kernel would do it. The modern kernel would probably go to a memory allocator like malloc, and we'll get a region of memory in a heap. It will be one global shared heap in a kernel. But here we use the data section. And just to illustrate my point, let me just quickly switch to the source code so I can show it to you. For example, here, if we go into the something like pipe.c, so this is the pipe alloc function, which allocates a new pipe. And what it does is the following. So it says, oh no, actually this guy, in case of a pipe, it allocates the whole page for the pipe. So it does actually allocates pipe dynamically. So I was wrong. So if I split into the something like a file.c, and I will do something like, okay, maybe it's too much just to split the screen here. If we do a file allocator, file alloc, so the way it works is that it has a file table which has some number of files. It's essentially just array in a data section, right?
The page should be available to both processes.
Right.
So we will be adding the page table.
Correct. So how does it work? Do you remember? That's a good question. That's actually a good discussion. So why? So it means that this inside process P1, let me change the color here so we emphasize what's important, right? That was wrong. Go ahead, undo. We don't have undo. Okay, so what you're saying is the following. Imagine there is a data section of a kernel, right? Imagine we have this file table with lots of files here, which we can allocate, right? And maybe like a process table with some processes which we can allocate as well, right? We are in P1, which drops with the right system call into the kernel, right? So at this point, it has its own user stack, right? It has its own kernel stack, right? And so it has some state on the stack, right? It has a process data structure, proc, right? Where's this proc data structure located? In the data section. So it's one of these, right? So essentially this is one of those, right? So how come this memory is mapped? Why is it mapped? Why is it available? Like when you try to access something like proc dot, I don't know, fd, for example, which is a collection of files, file descriptor. Correct. So this process on CR3 on this CPU on which we're running here will have a pointer to the page table, and it's like the page table is also like has a pointer here, right? Those the pages of the page table were allocated from the heap section of a kernel, right? So those pages are somewhere here. They're spread all over those pages, right? But they are mapped because we always mapped all the memory above the second gigabyte, right? Not all the memory, but above the second gigabyte and up to second gigabyte plus first stop, right? Which is roughly 200 something, I forgot, roughly 250 megabytes, right? That's how we start x86, right? And if we are in a different process which runs on a different CPU, for example, here, the CR3 of this CPU will also have a pointer to a page table of a different process, right? Proc, right? And this proc data structure will be somewhere here, right, in this table, which we're allocated. But again, the whole memory, this entire memory will be mapped by this second page table as well, right? And essentially, when you do a load here from one of those addresses, this cache line will be just bounced here to this CPU into the caching hierarchy of this CPU, right? Agree? So this explains how it works. So that's partially the reason, like, why, like, each process has access to the kernel memory, because kernel memory is shared across all of them, right? And the way they synchronize, they acquire log, because otherwise this problem of a linked list comes back, and we say, look, two processes on two different CPUs try to modify the kernel memory in some kernel data structures in some manner. Unless they synchronize, something bad might happen, right? So that's why logs are always there. Any other questions about this? We clear on how it runs? Okay, so back to a pipe. So pipe is reasonably easy. So, and I was wrong. So pipes are actually allocated, right? Because it uses pipe size, so 512 bytes. This is the buffer which the kernel maintains for each pipe in memory, in the kernel memory. So it comes with a spin log, right? It conceptually runs like that. So there will be two pointers, right? And if you have some unconsumed data, so marked as black on this slide, right? When someone reads the pipe, so there will be a pointer saying, okay, this is the last time you read something, and when you read some bytes, you update this pointer, kind of moving it here, right? And at some point you say, okay, my read and write pointers are the same, which means that I don't have any unconsumed data. So it works as a ring buffer. And similar, when you do a write, you say, look, I will essentially, if those slots were empty, I do the writes, updating like 3 bytes, and I update the write pointer to make sure that the next time I will be writing those bytes, right? And when you reach the end of the pipe, all these operations on those pointers, which are just simply numbers, they are implemented with a modular 512, meaning that when you reach element 512, it's the same as element 0, right? So that's why it's a ring buffer, right? So at any given point of time, the kernel can hold up to 512 bytes of user data, and users, that's why you say, remember, I was telling you, if you have a very big thing which you want to send through a pipe, you have to make sure that the sender and receiver run concurrently, because the sender will push max 512 bytes, but the receiver have to pick them up to make sure that there is some space is in the kernel buffer, right? So the sender can push the next 512 bytes, and sometimes it's less than 512, whatever the sender reads, right? That's clear? This data structure. This is the implementation of a pipe, right? And conceptually, you always just check for those conditions, right? So if the write pointer, which is this one, right? If it equals to the read pointer, it means that the pipe, the buffer is full, and if the plus pipe size, and if it just equals, then it means that the buffer is empty, because the both pointers point into the same location in this ring buffer, right? So the code of this pipe is the following. So when you have a pipe read operation which is implemented in the kernel, what you do here, let me just move this, you say, well, here's the pointer to the pipe, either pointer to the buffer, and here's the number of elements I want to read. Or, yeah, and so what you do here is you acquire a log, pipe log. Remember, each pipe has a log. And essentially you check for this condition. You say, look, okay, if the buffer is empty and the write end is still open, which means that you may get some data in the future, you just essentially, here you, okay, skipped a little bit first. So you release the pipe lock and you go to sleep, essentially saying, okay, no, hold on. If the process is killed, you just release the lock. If not, you go to sleep, passing this lock internally to avoid the lost wake up function, right? And here you will be, this process will be waiting on the writer to essentially send additional data. And so this write open, remember that when we were building the shell, we had this problem that you have to close the right ends of the pipe, otherwise the reader will never return, right? So this is why. So essentially, because of this check that it says, okay, there is a right end open. Visibly, there is a potential. Visibly, there is a possibility of additional bytes added to the pipe in the future, right? But so if you're reading from this process P1 and you still have an FD pointer to the right end of the pipe, then despite the fact that you went to sleep here, like it's a deadlock because it's your end. You will never write into this because you're sleeping, right? If, however, you say, okay, the pipe is not empty, you do the read by copying some bytes from the pipe and updating. So essentially, this is where you do the copy. So you're accessing the pipe ring buffer and copy them into this buffer which you passed along. And since you read some number of bytes and you keep counting how bytes you read, if you read just a simple byte, at this point you say, okay, I will wake up all the writers because maybe writers were waiting for some empty space becoming available. And at this point you release this, release the pipe lock. Question.
Will there be a bug on
Will there be a bug on overflow? Overflow on accessing
on the PMU
here? Yeah, but you're always accessing the pipe memory with the modular pipe size operation, right? So what happens when it reaches like the end of the address space? So essentially it's something like OX, FF, right? It's still okay. It's a little ugly to write this code this way, right? Because when you add 1, it turns into 0, 0, and so on, right? But it nicely worked because it's still 5. It's divisible by 512, right? So that will fly. Not the best way to write, I would say, but still works. So I believe there is no overflow in this code, but there might be if you take a close look, right? Okay, good. Okay, good with this. So these modular operations are reasonably frequent for those communication primitives. So pipe write is similar. So here you say, I will acquire the pipe lock, then I will try to keep writing into a pipe, incrementing the n is a counter or I is a counter of bytes I wrote. But of course, if the buffer is full, then what we do here, if the read open is 0, means that there will be no readers at this point. We don't have to write anything into a pipe. We will return -1. However, if we believe that there are some readers and we wrote some bytes, right? So we wake up the readers and then we go to sleep again, passing the lock as an argument here. If, however, everything is good, we keep writing bytes from the array which we got as an input into the pipe. And when we're done writing some number of bytes, we will wake up all the readers and release the lock at this point, right? So this is essentially, this is how the pipe is built.
So sleep and wake up the same as the one in send and receive, because the first argument p point to unwrite, is that the same data structure with the send and receive?
Right. So this is, I said the channel can be used loosely. It just essentially used as a number. If you remember wake up just compares the channel. So here we pass the pointer to this field P and W and right? And so it's the same field. So essentially, where do we have it? So pipe read, we will be reading. Okay, who do we? So here we wake up the readers, right? So, and the reader is actually sleeping on the same field, right? And here we wake up the writers, and writers are sleeping on this field, right? So it matches.
So the read and write the number will put into the process channel.
Yeah, yeah, exactly. So this field, which is interpreted as a channel, will be put it into proc channel. It's just the number, and we use the pointer as this number just to uniquely identify the channel. It's again, I cannot say that it's the most elegant way to do it, but that's one way to do it. We know that those fields are separate, different fields in memory, so we can use them this way. Good. Any other questions? All good. Okay, so done with pipes. So done with synchronization. So switching to file systems final. But again, so what we know up until now is, we booted, we're running the kernel, we know how the memory is mapped, we know how to create processes, we know how to bootstrap other CPUs, we understand why you need synchronization. We don't understand cache coherence very well, but we understand that the cache lines are moving back and forth between the cores, right? So it's pretty much a usable kernel at this point. So again, like if you are, like I yesterday was talking to a person, and that person says, okay, we're building a tiny operating system for a microcontroller, and that operating system was very, very like minimal. It handles some interrupts, kind of like Adreno style. Maybe it does a polling loop saying, okay, if sudden interrupt happen, we will react somehow. But I kind of argue with this knowledge of how x86 is constructed, you can transplant or port x86 and run it on that microcontroller. So despite the fact that there's two different classes, one is using embedded microcontrollers and we are using x86, the mechanisms are the same, right? So you say, look, it has interrupts, cool, I will be able to switch between processes. Maybe it doesn't have memory isolation. Maybe there are no page tables, for example. Well, we can give up isolation. Maybe we can create multiple processes and they will just share the memory. Like they can access memory of each other. That's bad. It might crash. It can be attacked. But nevertheless, it will run. You will have abstraction of a process, right? So for example, if you have something like alarms running, like a GUI running, showing you some time, which runs periodically, like you can implement it, right? That's kind of the high level story. So, and we know how to boot. We know that if we create a tiny memory allocator, we can allocate simple data structures for process memory, right? And pages are enough, or you can pick some other like unit of allocation, because if you don't have a paging unit, right? So like there is no virtual to physical translation, for example. That's just fine. But we say, okay, we can load L files from disk. We know where the data section is. We just load it in memory. If we don't have abstraction of virtual memory, so which means that each process doesn't have its own address 0, then we're going to do what? But we still want to run multiple processes. What's the solution for that? And you know the solution. Segmentation, if it's there, imagine there is no segmentation either. Very wimpy microcontroller. No segmentation. Like you just have physical memory, right? One physical memory. The kernel sits here with its like whatever data and text. The rest of it, you say it's a heap. You say I want to load an L file from disk. Like again, you know how to load files, like L files. You say I loaded the data section and the text section of this process, right? Maybe I left some space here for the heap if we want to have continuous heap, right? But this one is no longer 0, it's some address A, right? Then you load another L file, and it's another process. Maybe this one is a shell, and this one is, and a WC again. You load data text, left some space for the heap here, right? It's not address 0 anymore, it's address B. But I argue you can still run successfully, but the only thing you need to do is what?
Position independent.
That's one way to do a position independent code, essentially. Or another way is just simply do a relocation step. So you don't even need position independent code. Just when you will load the L file, you see, look, I I know that you linked to run at 0, but I will quickly relocate you, meaning that there is a table which says, okay, patch this location in memory, adding some offset, which is like in this case A, and then everything will be fine, right? So that's the relocation step. So you don't really need virtual memory to get it running, right? So it will be just fine. That's my point. Oh, well, it may happen that this process is so bad that it just writes something into the text section of another process just because you made a mistake, right? Then that's bad, but not too bad. If you use some technology like WASM, WebAssembly, then you can enforce bounds on the process and you can catch this right even in hardware or even just in software with no page tables, right? Is that clear? So essentially, my point here is that you, at this point, like if you look back a little bit and like think about the pieces which you can build your own tiny operating system again, like you have an interrupt. Maybe it's not an interrupt descriptor table. Maybe it's something else. Maybe you just register interrupts with this microcontroller. I don't know how it runs. But nevertheless, you understand that, the timer will be delivering an interrupt. You will get into the timer handler. Wait, timer. Timer can go into the scheduler. If the interrupt save everything on some kind of a stack here, then you can context switch between the processes, right? So that's my message. So you're there. So one thing which was not yet covered. So this kernel is it's pretty powerful, like POSIX subset. So that's pretty cool. What we haven't done yet is this loading step, right? We don't yet know how to read and write files. We don't even know what these files are, right? We kind of we use them. We use this reading from an inode, right? But we never looked at how to build them. So that's our goal right now. Okay, let's do it. So we have this file systems lecture. Okay, so if I ask you, how would you implement a file system? What would be your answer? A tree. A tree which does what?
Well, it throws a bunch of blocks of size and then files. You like the root is the root of the tree. Have it not like that.
Well, kind of. But there are multiple levels, right? So if you have a disk, imagine this is the space of a disk, starting from 0 to some max, right? Like that's on disk. When you say readme block 0, the disk controller will read you these 512 bytes, right? What we typically want from a file system is multiple things. So we need something like a human readable names like bin, user, right? And so on, home. It's just convenient for us as people to organize information this way. You say, look, like if I'm working on a project x86, I will create inside my user home I will create a folder x86, right? And I will put a collection of files which are relevant to x86 or related to this project into this spot, right? So on social media, we now use, instead of this name, we just use a hashtag, something like x86, right? And which doesn't give us a hierarchy, but we know that those things are still related to x86, right? But then it's kind of a distributed thing, and anyone can add any additional things here by marking them with this hashtag. But we can, typically what we want to do is to maintain this naming structure. It's called a directory structure, right? But individually, each file, each of those guys, we maintain as files, right? And those files, which have a name inode, are essentially like the actual data. It's spread somewhere on this disk, right? It's not continuous because the files are growing, right? So you just say, okay, some blocks will represent this inode. So typically what you do is you maintain, like you say, a tree. So there is a couple of trees. One is this directory tree, and the second tree is this inode, which essentially just holds the mapping. So it's the block 0 of this file, so essentially file block 0 is, I don't know, block 512 on disk. Block 1 is block 65 on disk. Block 2 is block, I don't know, 1023 on disk, right? So that's another tree, and this tree can be growing when you say, okay, please, I want to write block, and imagine these blocks are 512 bytes. I want to write a block 3 here, right? You add an element to the inode and remember how this block 3 is mapped, right? Agree with this? So that's the high level idea. So let's just go step by step through those elements. So two main goals: provide some sharing, because we have one disk, but there will be multiple users and multiple files, right? So this single disk, it's kind of like a single physical memory, but it's a storage memory, right? And it's shared between multiple files. Second, we want to provide persistent storage, which means that this data is available after reboot. So which means that if we update one of those data structures, we always have to write them back to disk to make sure that after reboot, it's again available to us, right? So which at a high level means that there will be some on-disk and in-memory data structures. When we open the file system, try to read and write it, there will be some collection of the data structures in memory, which will help us to avoid the latency of going to disk every time we do a simple read or write on a metadata, like for example, trying to read where the block of a specific file is located on disk, right? But at the same time, all these data structures will be backed up by their kind of equivalent data structures on disk, because if we lose power, we're going to reboot and reread those data structures again, right? Which means that we also have to support something what is called crash recovery or atomicity, meaning that if you do even a simple write into a file, maybe you're allocating new blocks to add to this file. So your memory allocator, which keeps track of which blocks on disk are available and which are already used, has to be updated. Maybe you give this file a name, and which means that the directory tree has to be updated. And this inode, which holds the mapping between the logical position within the file and the block on disk, has to be updated as well. If you doing those updates like 1, 2, and then suddenly lose power, you reboot, you come back into the inconsistent state. So for example, one block will be marked both as free and at the same time is used somewhere, right? So then you will allocate it again. It will be like used from 2 different files, for example, and they will write one on top of each other, right? So which means that those updates have to be atomic. The group of updates is either happens, all of them happen, or none, right? So you kind of have to build an abstraction of a transaction, right? And second, we, especially in the past when the disks were super duper slow, we have to make sure that we don't go to disk every time we try to read or write something. So essentially the file system maintains a cache of blocks in memory, meaning that you can do multiple writes into a block, and at some point you flush this block back on disk, right? So it will, like, it's very similar to how a cache line is brought into the first level cache, and the CPU does multiple reads or writes on the cache line, and then it is demoted into the second level cache, third level cache, and then goes back to memory. So similar happens here. So from memory, which has a latency of roughly 200 to 300 cycles, periodically you flush those blocks to disk, and the disk used to have a latency of like 20 million cycles. The spinning disks still have the same latency, but modern NVMe solid state drives, they have latency of roughly, let's say, like, I don't know, 4,000 cycles, and it's the fastest ones. So some of them are slower, like let's say 4,000 to 10,000 cycles, right? So it got better, but it's still slower than memory, right? Okay, so if we want to build those ideas, we build file system as this hierarchical structure. At the very bottom, there is an abstraction of a buffer cache. So it's essentially, this is the cache which, like, once in a while reads something from disk in memory and keeps it around, right? So it says, okay, I read block number 75 and I have it in memory. If you want to write into block or read block 75, you can just read and write memory. And later I will flash it back to disk, right? So the buffer cache provides this speed, but also it synchronizes accesses from multiple processes, because multiple processes can open the same file with an open system call, right? At some point you say, okay, well, who has the turn to write? And so buffer cache provides this abstraction. So there will be some kind of a synchronization similar to spin locks at the level of a buffer cache. Above the buffer cache, we have this journaling or logging layer, which implements this transactional semantics, right? So it groups multiple updates into a single atomic transaction, and it's either happens or not. And it's a little bit harder to build than it looks like, because, and I don't know, maybe if you took the database classes, then you know how to build transactions. So, but it's usually a little challenging. Above this, there will be a layer of inodes. Inodes are essentially mapping from the position in the file to a block on disk, but they don't have names. They only have numbers like 1, 2, 3, 4, 5, and so on, right? And we've seen the inodes, right? But for humans, operating with numbers will be a little bit too much. That's why above this level, we have a level of a directory. So essentially, a directory remembers that it has multiple inodes, and it actually gives each inode a name, like foo, bar, and so on, right? Above this, there's a level which resolves paths into actual specific inode. So remember, it starts from the root, descends into the user directory, descends into the bin directory, and figures out an inode inside the bin directory, which has the name sh, right? I will explain how to build those. And at the very top, we just have system calls, so essentially open, close, read, write, and essentially checking of arguments to make sure that the users don't pass any obscure buffers, right? Again, high-level overview. Let's just dive a little bit into the details. This is the layout of a system, one possible layout, and this is the one which is used by x86 on disk. The block number 0 contains the boot code. This is where the BIOS essentially reads the memory from to make sure that it moves it into this 7C00, right, and jumps to the beginning of it. So block number 1 contains something what is called a super block, essentially metadata about the file system itself. And roughly what it says, it just tells you the sizes of those sections. So it says, okay, I have a total size of a file system in blocks, number of data blocks here, number of inodes here, number of blocks in the log, and such stuff. Like essentially, when the operating system opens the file system, right? So for the first time, it reads this metadata and understands, okay, I know what I'm dealing with, because different file system might have different sizes. I mean, even the same file system, we have just one implemented in x86, might have a different parameters which control the number of inodes, right? Because here, this section, this number of inodes, for example, will limit how many files total you may have in this file system, right? And if you have a file system with lots of files, you might want to have this section a little bit bigger, right? Okay, so this log area is used by this journaling mechanism to implement transactions. So it's kind of like a scratch pad. Inodes, essentially, I said inodes are unnamed files. So essentially, this one is split into the equal chunks. Each one is an inode. Remember I said there will be on disk and in-memory representations of inodes, but essentially when you power the system down, everything what you note here is that you know the inodes are here, and then they will lead you to further directories and stuff like that. But this is the array of inodes, which you know by the number, right? And each inode is like a tree, essentially says, I will have some metadata, and essentially you say address 0, it's a pointer, essentially says in the disk block 17, for example. Block 1 is in block, I don't know, 25, and so on. So you have a little bit of those. So 12, those are called direct blocks, which, because you say for small files, that's enough. Maybe my file like this has less than 12 multiplied by 512 bytes. So, but if you run out of this, then there will be a pointer to a block 512 bytes. Each contains, like divided by 4, you will get 128. Each contains essentially addresses of recursive blocks, right? So the total number, if I ask you a question, what is the max file size supported by x86? So we have 12 blocks here, right? And then how many? And 128 here. Right, so I think it's 12 plus 128 multiplied by 512. That's the max file size which x86 supports, right? It's not bad. Then we have an area of disk which is essentially a bitmap block allocator. So it says, okay, it contains a bit for each of the blocks in the data section saying if either available or free, right? And the allocator, which says, okay, I need a new block, will be essentially scanning through this bitmap, trying to find the free element on disk, and then essentially marks it as allocated and just returns this as a number, 75, for example, to whoever wanted to allocate a new block. It might be added to the new inode, to the inode which you like into which you're writing, like essentially, or right. And this is the actual data area where you contain the actual data on disk, right? So any questions about the layout for now?
Can we use a hash map instead of the tree line?
Can we use a hash map? Okay, good question. So who can tell me? Hash map here, right? So essentially what you want to do, you say, let's, for example, use those cells as a hash map, right? Is that what you want to do, or something else? You can use hash maps in many different ways, but the question is like, what is it you want?
The directory, the instruction that maybe we just take a string and define this hash map and find a block.
I mean, the short answer, yes. Let's maybe cover first how x86 builds the file system, and then we can talk about how we can optimize where we can plug hash maps and stuff like that. Yeah, you can come up with all sorts of tricks. Hash maps are fine, but there are trade-offs, meaning that they provide constant access time, right? For one. The disadvantage is that they might need resizing, right? When you run out of, like, you either overallocate space, overcommit space for the hash map, right? Or you have to handle conflicts, which is possible, but you need this discipline. And sometimes, depending on how you're handling the conflicts, you might need resizing or additional allocator as well, right? It might give you some benefits, but like you have to be careful.
The bit mapping part of the file system, is that representing the same is in memory at all?
We'll see how it works, but essentially when you do something like block alloc, the function essentially says, okay, I will start scanning this bitmap. It will do a block read of the first block in the bitmap area. We'll scan it when this block will get into the buffer cache and will be represented by 512 bytes of memory. Then you do the scan on this one. If you do find it, you're done. And since you will do a block write, right? Because at this point you changed the 0 to 1, for example. And at this point, like, this block will still stay in memory, and if someone else will try to read it again, it will just hit it in the buffer cache. Will keep scanning. At some point, this block will get evicted back because you say, I ran out of space in the buffer cache, and then it will be written back here, right? Back on disk. Yet you have to maintain atomicity because you say, look, I cannot like leave this guy for too long in memory, because what if I crash, right? Then next time I will come, the copy on disk and copy in memory like diverge, because maybe I did some other writes like to the inodes or to these areas, right? So that's why you typically wrap it, you not typically, you always wrap it in something what is called a transaction. And when transaction commits, you make sure that this block is written back to memory, back to disk. So we'll get to that in a second. Okay, go ahead with the next question.
Well, I guess I'm just wondering, like, the representation, so basically, because we're like memory allocated.
Right, lists. So here, again, that's a very good observation, because obviously as your file system is growing in size, since you're doing a linear search here, your performance drops considerably, because every time you allocate a new block, you have to scan through all the blocks before, right? And it's an observable. We used to have this homework where we say, okay, show us like dots, like how long it takes you to read and write a file, and suggest an optimization. And one optimization would be like maintain some kind of a hint saying that, okay, this is the last time I was from where I found the last empty block, so let's scan forward. That works up until a certain point, because later on you will have fragmentation, and then like used and unused bits will be all over the place, so it doesn't work that much. And then you say, okay, my next optimization is probably introduce a linked list into this block. And of course, it's a very good optimization, because your allocation time now is 01, right? You just fetch a link, like an element from a linked list, but you wasting space, because now you have to, instead of wasting 1 bit, instead of using 1 bit per data area, and this data area is kind of giant, you now have to like use at least maybe 32 bits, because it depends on how many elements you want to. Maybe it's 16 bits, maybe it's 32, maybe some other number in between, maybe larger. But then, okay, you kind of say, okay, I'm trading performance for space, which is not always very good, because if you maintain a ton of those, and then you say, okay, my next round of optimization will be something like in between. I will have like a collection of bits, and I will maintain those empty and allocated bits in some kind of a list as well. So that's how you evolve essentially. And as long as you understand what you want, it's usually easy to express, and then you start talking in terms of optimizations. These days, those guys who do this, talk to Prashant. If you never met Prashant, he's a professor here who builds those, and he built a couple of those extremely large file systems, petabytes probably, and they use those epsilon B trees. Like it's all sorts of optimizations to essentially address those problems.
I'm just wondering why did x86 Germany not have larger files? Do you have any idea with that?
It's just a design choice for specifically. I mean, journaling is essential for atomicity, so it's very hard to build a file system without a journal. And I will explain how journal works, because for most people it's probably hard to understand at this point. Alternative technique is to very carefully reason about the ordering of writes, kind of like create a tree of writes and apply the last write, the top of the tree as a last write, meaning that it either happens or not. You can do this, and this technique is called soft updates, and FreeBSD uses this technique in its whole file system, and some other research work was using it as well. But journaling is simpler, easier to reason about, easier to get correct, and at the same time, it illustrates the trend in modern file systems. Although, like, it's an open question which one is really better. So I'm not arguing that one is better. So for educational purposes, they limited the size of the file system to this. Our homework, which is historically we changed it slightly, but it was different implementation of these data structures, either like add more levels to this tree to make sure that you can support larger files, which is typical in like ext3 file systems, or maintain some kind of a linked list, essentially, like instead of doing a tree, have a linked list here. And this, I think, FAT file system, which was used by Windows, was doing this trick. So essentially that was assigned as a homework, and hopefully will be assigned as an extra credit exercise to essentially build one of those mechanisms. We just change because okay, there are so many of them you can build, and like you can find them online, so it's not very hard to Google. But essentially, like, the idea is to force you to understand how everything works through the process of changing this layout. Okay. Okay, let's get at least to the buffer cache, because we need to move forward. Okay, buffer cache is the bottommost layer, right? Two goals. Synchronization means that only one copy of a data blocks exists in memory, and in any single moment, only one writer is allowed. So it's very kind of similar to cache coherence protocol, you know, multiple readers, single writers, or what is it? Concurrent readers, exclusive writers, crew, right? So same idea. Multiple processes can read a block, but if one process wants to write, then it has to wait for all the readers to exit, right? And caching, essentially. Frequently used copies are cached for fresh reads through in memory, right? So the buffer cache itself is an array. So essentially, it's array of buffers, right? And buff. And each buffer is actually represents an entry in a buffer cache, right? So the entry in a buffer cache itself is like the main point is data. So 5/12 of bytes, right? So this is the data. Some flags to reason about the state of the buffer, like of the element in the buffer cache. So it can be busy, valid can be dirty, meaning that it was written and has to be flashed back to disk, right? It has a device ID, meaning that we have a single buffer cache in the system, but maybe we'll have multiple disks. And so when you flash it back, you know which disk to use, right? Typically, when we boot x86 boots with only one, this is how we configure our QEMU emulator, but you can boot with multiple disks, right? The block number itself, because you have to know where to flash this data on disk, right? So block 75. And an interesting bit here is we maintain the least recently used list, right? Meaning that the eviction policy is LRU, meaning that if the block was not used for a long time, it's a good candidate to get evicted, right? And it's a doubly linked list. Every time we touch a block, we promote the element to the front of the list. And when we need to evict a block because we ran out of space, we'll look at the tail of the list and essentially evict this block, right? So, and here it's, like makes sense. So it's a good policy. Okay. The interface of the buffer cache is the following. So it has the block read and block write functions. It has another function, brelease, which allows you to release a block. So these two functions essentially acquire a lock on a block. And essentially the block is owned until you explicitly call block release, right? So for example, when you attempt the read a block, so for example, higher levels of the file system try to read the block, they provide the ID of the device and the number of this block on disk, right? So that's essentially if you have a disk space, like this is on disk, you say, I want to read the block number 75, that's your 75 here. What you do here is you invoke this block get function, essentially passing this as arguments, right? What the back block get internally does, it essentially tries to first check if this block exists in a buffer cache. It's a very naive implementation. So it's a linear search of the buffer cache. So essentially it goes to the buffer cache linked list. So buffer cache essentially, remember, so if those are the blocks, they are maintained as doubly linked list. And it starts from the head, right, and goes forward. It checks whether the device and the block number matches, right? If it matches, it means the block is found. And at this point, it checks whether the flags are not busy, meaning that the block is not used by anyone. If it's not busy, you set the busy flag here and you release the buffer cache lock. Note that the entire buffer cache is protected by one giant lock, which enforces this atomicity across multiple processes on multiple CPUs, right? So, and you return this block and it's already in a busy state owned by you, right? That's what you return here. If, however, the buffer cache was busy here, then you go to sleep, providing this buffer cache lock as an argument, right? When you will get woken up later on, you will try to essentially like restart from the beginning because the block could have moved because every time we touch a block, we promote it to the beginning, so we have to restart the search. But at a high level, okay, it works as a cache, right? Everyone agrees? And a little naive, so kind of like linear search is never good. The second case is if the block is not found. So essentially you search through the entire list and you never found a matching block. So what you do at this point, you say, okay, at this point I have to find a spot, an empty block in the buffer cache, which means that, okay, yeah, sure, like because I want to read a block from disk. So what you do here again, you start searching in a list for the buffer block in a cache which is not busy, meaning that it's not used by anyone, and it's not dirty. If it's dirty, it has to be flashed back to disk, so you cannot really reuse it, right? But if not dirty, then you say, sure, I will use this block and I will use it for my new block number. So you update the device and update the block number, set the busy flag, release the buffer cache lock, and return this block. This block does not yet contain valid data because you just allocated the block on disk or in the buffer cache, but you never read it from disk, right? It might be a new block, right? However, what you have here is when you get this block, you account for those possibilities. If the valid flag is set, then you're done, right? If it's not set, you go to the disk controller and read this block. Essentially, at this point, the block is read from disk and the valid flag is set. And at this point, you return it to the user, right? At this point, you cache the valid data in memory. Agree? Again, kind of simple, but worth probably going through. So a release is when you're done reading the block or writing the block, you use the release function, block release. You again acquire the global buffer cache lock to avoid any races. You promote the block to the head of the list because you just used it, so you put it in a very beginning of the list, and you essentially say, okay, I'm removing the busy flag, and I wake up everyone who can potentially be waiting on this block, right? Because people might be like, maybe someone is essentially waiting for this block to because it tries to access the same block, right? And a typical pattern of accesses here is that you do a block read, maybe you do an update with block write, and then you call block release, right? So this is the typical sequence. So here is an example when you we will cover this function, which is it's part of the journaling mechanism. So, but essentially it reads two blocks and copies one block into another. So it first reads one block, reads another one, it writes one of them, right? Second is not written just because you do this copy, and you release both of them, right? So not surprising. This is the API, how the file system uses the buffer cache. Okay, so probably good time to stop here. We'll start with journaling and we'll finish the file systems next on Thursday. And then next week we'll have a review and then a file now exam. Thank you.